When we are trying to give a name to a compound that is ionic, in other words, a compound that has a charged metal and a non-metal in most cases, there are certain rules that we follow because in nature there are some metals, which are those the elements on the left side of the periodic table, not counting hydrogen, of course, that have only one possible charge. We often call these representative metals. And that is the alkali metals such as lithium and sodium, potassium that always have a positive 1 charge, alkaline earth metals which have a positive 2 charge, and then some of our positive 3 metals on to the right, on getting more to the right of the transition metal section like aluminum and gallium. But then other metals, particularly those that are found in this zone, known as the D block or the transition metal zone, can have more than one possible charge. There are some such as manganese, which have a whole lot of possible charges, a +2, +3, +4, +6, +7, or like iron, which only has normally a +2 or a +3, only have a couple of possible charges. So when we have a couple of ionic compounds like we have here, we have to first look, is there a transition metal? In other words, is there more than one possible charge to this metal? In the case of magnesium chloride, no. So we just give it the name metal plus anion, magnesium chloride. We take the chlorine, and because we're wanting to show that it is put into an ionic charge of -1, and we have 2 of them, we change the chlorine to chloride. We do that I ending for anions that are monatomic, that they have only one element represented. And we can verify that magnesium fits this rule because it's an alkaline earth metal, so it's representative like these other elements here. However, when we take a look at iron here in what is some form of iron sulfate, we see clearly that he is a transition metal. And reference sheets will list the common charges as being a +2 or +3. So we need to know which one is it, because that is important in doing all kinds of meaningful chemistry with this substance. Iron 2 sulfate and iron 3 sulfate are 2 completely different substances that will behave differently chemically, that will have different boiling and melting points and so forth. So it is relevant. We can't do meaningful chemistry unless we know which form it is. So we see here a series of steps to get us to identifying whether we're looking at iron 2 sulfate or iron 3 sulfate. So we have established that yes, there is a transition metal here, and we'll follow this 5-step path. So the first thing we do is we always solve for the total charge of the anion first. And so that is done by step 1, finding the charge. The anion sulfate is a very common polyatomic. You look on the reference sheet, it lists it as a -2 charge. And like all anions in nature, in almost all settings, its charge does not change. It will always be 2-. So we know that if we take that charge and multiply it by the number of particles, we can find a total negative charge. And then in this case, the charge is -6. The next step is that we set the other side, the positive cation side, to +6, the opposite, because all compounds must balance positive and negative out to be electrostatically 0. So once we've done that, we simply take that total and divide by the number of particles, and that gives us the formal charge. And you can see that it works backwards and forwards. That is a division or a multiplication. Both sides should equal 6, +6 to -6. And then finally, that positive charge that we've derived from these steps becomes the Roman numeral in the name. This becomes iron 3 sulfate, as opposed to FeSO4, which would be iron 2 sulfate. So in closing, you have to learn a few basic logical steps to determine first if we need to use a Roman numeral in our ionic compound name to describe a particular transition metal charge or not. And that's what we did here. And then once we have established that there indeed is a transition metal with more than one possible charge, we go through, we're basically solving for the total charge of the anion side first, because anions are stable in carrying a constant charge. They will not change like transition metals can. Once we have done that, we can apply the opposite value for total charge, and then take that total charge for the positive side divided by its number of particles, and then we have a charge for one individual particle that we give as the Roman numeral identifier for the identity of what form of that particular compound we have.